Hey Forensic Science, this lesson is going to be talking about exactly how we test for drugs. So to start off, the goal is we've got this unknown drug, this unknown poison, for example, that we're trying to figure out what it is. And we're going to go through the process of how is that done exactly by a forensic scientist. First of all, there's the observations, macro and micro, right? So in other words, macro, you look at it with your naked eye in the senses. Micro, check it out under the microscope and see what you can tell from there. After that, you can do some presumptive testing. We've seen that before, right? Do a test that gives us a simple yes or no. Is this marijuana or not type thing. Then we also have our more definitive tests, again, just like we talked about in the arson unit. So we have our gas chromatography. That should sound familiar. Used to separate mixtures. And our mass spectrometry, used to actually identify specific molecules. And then there's a new one called IR spectroscopy that we'll be examining as well. So, chromatography, as we've said in the past, is a separation technique. It's used to separate a mixture of different substances. What we haven't talked about yet is the paper chromatography part, which we'll get to in a second. So how do we use this? Well, in forensic science, we have all kinds of uses. We know we use it in arson. We talked about that, identifying accelerants. It's also used to separate out the mixture of drugs, right? So often drugs are cut with other substances in order to increase the quantity of the product made. So a drug dealer will add other substances to the drug to make it less pure so that they can get more money per gram when they're selling it, right? So there'll be other stuff in there. It's hardly ever just a pure drug, for example. It's also used to separate drugs and poisons from bodily fluids, to isolate them. And it's used in inks as well for forgery analysis. So in other words, comparing the original ink from the original artwork or ink signature and comparing it to see whether something is fraudulent or not, see whether they separate the same way. And airports use this for explosive residue and arson as well. So a couple different interesting uses for the separation technique. The paper chromatography itself, the way that it works is that, let's say this is similar to your paper that you're working on. And so you take the sample, take a concentrated dot of it, whatever you've got, this mixture that you've got. You can actually do this with a Sharpie marker as well, because that's actually a mixture of multiple different substances to make that black ink. But yeah, so in this case we've got a sample of what could be marijuana, we're going to see. Take a concentrated sample, add it to the bottom, and then what they've done is they've taken this gel and they've put it vertically in this chamber, and they've added a specific type of solvent, so a specific type of liquid that's designed to go with this substance to maximize separation. So essentially they put this in here like this with the solvent at the bottom, and they let the solvent travel up the gel we're looking at, or if you're doing it with paper, with that. And so as it's traveling up, it'll pass through that concentrated dot that was put there, and the various components that make up that mixture that was in that dot will begin to separate at different rates. Some of them will get left behind. So here's actually the results for marijuana on the left and on the right. So the dot started down here, the original dot. This is where they began. The solvent was down below here at the bottom, and it traveled up, just kind of absorbed through this filter here. And the various components of the mixture separated. Now, we knew that one of them at least was marijuana, and we're looking at maybe our unknown, for example, and they both separated it out the same way. Because remember, marijuana isn't just THC, for example, there's other components. And so both of these separated out the same way, so we can say that this looks a lot like marijuana as well. But the point is, again, chromatography being a separation technique, one version of it is paper chromatography. The version we're more familiar with, right, was the gas chromatography, and it is analogous, very similar to the paper, in that, but instead of using paper, this column has all kinds of other substances inside of it to again try to filter, in this case, gases. So we know we inject the gases, they pass through the column, and they're separated, and then depending on their chemical properties, they come out at different times, right? So some substances will come out faster than others after the gas chromatography is done. We remember that from before. So same kind of thing, just slightly different. And of course, here's our giant gas chromatography machine we talked about in the past. And here's an example. So remember, this time we're applying it to drugs. So just here's a couple of mixtures of drugs that have been separated. Remember, it's retention time, right? So how long did it take for it to pass through the column? And for example, the pentobarbital came out earlier than the secobarbital. So again, this is just a separation technique. It's not an absolute means of ID, right? So it's not guaranteed this is exactly what you're looking at. So that's why we do the mass spec and the infrared spectroscopy we'll be talking about, because those are more definitive. They'll tell you more exactly what you've got, essentially. Sometimes gas chromatograms can come out similar for different mixtures. So mass spec, just a quick recall, remember that in the arson unit we talked about this, and we said that you take your chemical, like in this case this is acetone from the arson unit, but you do this with drugs as well, and you bombard it with electrons, and it breaks into pieces, and those pieces register based on mass. So all the way on the right, you've always got your biggest piece, the whole piece essentially, and then as you go to the left, you get the smaller chunks that were created as a result of this electron bombardment, and they're separated by mass. Remember as well that the mass spec, instead of looking like kind of hilly peaks, it's got like just vertical lines that are like perfectly vertical lines that that represent mass spec. So none of these have any width to them, essentially. And we said that this is like our fingerprint of the substance, right? So you can tell exactly what it is based on the mass spec. So again, we're talking about drugs now. So here's the mass spectrum for heroin, and here's the mass spectrum for cocaine. And heroin always makes this signature, cocaine always makes this signature. So that's how we tell. We compare our spectrum to our known spectrum of heroin, and if they match exactly, then this must be heroin, for example. And we remember that we often use these in conjunction, right? So the gas chromatography is used to separate the mixture. We get these different peaks. Here's our mixture. And then notice how they're separated out and analyzed separately for the mass spectra that they produce. So here's the mass spectrum of A, the mass spectrum of B, C, and then D. So again, these analytical techniques look different, and this is a separation technique for mixtures, and then this is an actual definitive test that tells you exactly what you've got for individual substances, one at a time. Okay, so let's get to the infrared spectroscopy. First thing, and we don't want to know all of these details, we just want to get the general idea about this. Infrared light is a region of light that has certain wavelength, right? So certain distance from wave to wave, and certain frequency associated with it. And there's a range of infrared light kind of frequencies that you can have. So, for example, you can have shorter and longer that all fit within what we call the infrared range. And what we're going to be looking at is that we apply specifically infrared light to the substance, and then the substance will either absorb that light, portions of that light or not, and give us a certain output, which we'll be checking out in a second.
What you see here is the molecule formaldehyde. And formaldehyde just so happens to have something called a carbonyl functional group. That is simply the C that's doubly bonded to the O. We call that a carbonyl functional group. What we need to understand is that if you actually have a sample of formaldehyde, it's not static like what you see here. For instance, let's represent the oxygen right here as some kind of sphere and the carbon also as some kind of sphere. And the double bond between them, let's represent it as this single bond right here. If you were to actually see a formaldehyde molecule, you would actually see the carbonyl bond do something like this. It would actually stretch and compress like this, almost as if there is a spring between the carbon and the oxygen. But that's not the only thing this carbonyl can do. It can actually do something like this, move back and forth like this. In organic chemistry, we call that wagging, kind of like the tail of a dog. So this is the reality of the carbonyl group in formaldehyde. What we've seen is that it can stretch, or have what's called a stretching vibration. And let's do this. Let's make up a number. Let's just say it happens to stretch at a frequency of 2 Hertz. Now, what does that mean here? Remember, Hertz is a measure of cycles per second. So if this is stretching at 2 Hertz, it basically means this right here. Let's say we start at this position. The 2 Hertz means that it'll stretch 1 like this, and then 2 cycles per every second. Now, keep in mind that's not the reality. It actually vibrates at a much, much higher frequency, but let's keep the number simple for now. Now, let's say we could also measure the wagging. And let's happen to say that it wags at 4 hertz, which again, it means it goes back and forth one cycle, or wags back and forth, 4 times per 1 second. If that's the reality, then let's see what happens when we take our formaldehyde molecule and we stick him in the IR spectrometer. And let's again label our stretchings at 2 hertz and our waggings at 4 hertz. So here is how the IR spectrometer functions. What happens is when the molecule is in the machine, we take something like this, a light source, which is simply something that has the ability to shine light at a molecule at various frequencies. On the other side of the machine, we have this thing right here, a detector. And all he can do is detect light. Now, imagine this for a second. Let's say again our light source has the ability to produce light at various frequencies. So let's say we set our light source to deliver a light that happens to have a 1 hertz frequency. If we shine this 1 hertz frequency light at our molecule, it'll go right through the molecule and hit the detector. And the detector, of course, would say, when you shine 1 hertz frequency light at the molecule, I detected it. We'll see why that happened in a second. But for now, let's graph what we see in front of us here. If you had a graph with, let's say, on the y-axis, the percent transmitted, and this means the percent of light that transmits or moves through the molecule, which would obviously run from 0 to 100%. And let's say for now on the x-axis you put the frequency of light. So the graph of what we just saw here would look like this. At 1 hertz frequency light, 100% of the light went through the sample and the detector detected that light. Now, let's see what happens if we go back to our light source and now let's set it at 2 hertz frequency light. If we shine this at the molecule, what's going to happen here is the molecule will actually absorb light at that frequency. And this right here is key to understanding how this machine works. Notice the frequency of the light that's being absorbed, 2 in this case, matches the frequency of the stretching. When these two things match up, the molecule will absorb the light, which means think about the detector here. His observation is that when you shine 2 hertz frequency light, he doesn't detect the light at all because it was simply absorbed by the molecule. Let's see what this would look like on our graph now. Again, at 2 hertz frequency light, the detector would say not very much transmitted through it. A lot of it was absorbed, so we have a small percent that's transmitted. And that would be this point on the graph. Now, let's go back to our machine here. Let's now take our light source and set it at this time 3 hertz. Think about what we just learned here. If this molecule stretches at 2 hertz and wags at 4 hertz, then when we shine the 3 hertz frequency light, it should go right through it. There simply is no match in this case. And the detector therefore would say 100% of the light transmitted through the molecule. So again, going back to our graph right here, we would see that this would be the graph at 3 hertz frequency, 100% transmitted. Now, while we're here, let's do this. Let's connect these dots. This is what we would have.
So what we're looking at here is actually the infrared spectrum of ethanol. Ethanol is the chemical name for drinking alcohol. Of the types of alcohol, this is the kind that won't kill you immediately if you drink it. And so what we're looking at is, it's important to look at infrared spectrum from the top to bottom. You're looking at these peaks that are coming down. So you're not looking at it down here and then looking up. You're actually looking at these peaks that start up here and then come down. I always think of it like the stalactites that hang at the very top of the cave. And that's what we're looking at here. And so ethanol is called ethanol because it's got 2 carbons, like we talked about before. That's where the F comes from. But pretend you didn't know that. Pretend you didn't know what this structure was or what it was called or anything like that, which is often the case with these drugs. Maybe we don't know what's there. The forensic scientist will look at the infrared spectrum and they'll look at the peaks, and each peak coming down from the top will tell us different things. For example, these peaks represent a C-bonded O stretch. So if a substance has peaks appearing here, there's a C bonded to an O somewhere in the chemical structure, which that's what we have for ethanol. There's also a CH peak that we see. So this peak would tell scientists in this region that, okay, this goes with CH. There's a CH somewhere in the structure. And then we also have an OH stretch represented more on the left here, which there's an OH here as well. So scientists combine all this information in order to determine, hey, this is the chemical structure. And they're also going to compare it to their known infrared spectrums of ethanol and say, yeah, this matches ethanol, we've got ethanol in our hands type thing. So remember, the general idea of how this works is that infrared light is of various frequencies, is passed through our unknown substance. The substance will absorb the frequencies of infrared light that coincide, that happen to vibrate at the same frequency as the bonds. So we had an OH bond, CH bond, and CO bonds that all appeared because they vibrated at the same frequency of these different peaks, essentially, of that particular region of the infrared light. If it doesn't match at all with the incoming infrared light, then it won't absorb it at all. It'll just transmit completely. So notice it says transmittance over here. That's kind of a giveaway for infrared as well. Okay, so we've got our infrared spectrum of heroin, and this is the one for secobarbital. So again, we're taking this and applying it to unknown drugs. Heroin always looks like this. Secobarbital always looks like this, so we can match these spectra. And again, this is like the fingerprint of the substance. So a spectrophotometer is just the name of the device that spits out this output. It's the name of the fancy machine that's going to measure the quantity of radiation that the molecule absorbs. It's going to see how much infrared is actually absorbed by the chemical and give us an output based on what types of infrared were absorbed and what types were not absorbed. And each molecule is going to absorb energy at different specific frequencies. Okay, so here's the end. So just a quick summary. Remember, gas chromatography GC looks like this. We've got our peaks from the bottom going upwards. It separates full mixtures. It's a separation technique. Mass spectrometry, oh, and we've got time in the x-axis, right, because it takes a certain amount of time for the mixture, each substance in the mixture, to pass through the column. Mass spectrometry breaks up this only one substance. It's only analyzing one substance at a time, breaks it apart, and it separates based on mass, and the lines are perfectly vertical. So that's how we know if we got mass spec that we're looking at. IR spectroscopy actually has the peaks coming down from the top, and one giveaway for that is that on the left it says transmittance, because it's based on how much was absorbed by the chemical and how much was transmitted because of that. Okay, thanks for watching. Let us know if you have any questions on these testing techniques for various drugs.